disjoint sets with union data structure. Okay, so the problem that we have is a very simple one, and you might have seen this many times before. We have a set of n elements. So let's say I have n elements, and I'm going to call them just 1 to n. And they are in a bunch of sets. Initially, each element is in its own set. So I have one set for element 1, one set for element 2, and so on, all the way to n. And we should support two types of operations. The first type of operation that we want to support is to merge. So we are given two elements, let's say x and y. And what we want to do is to merge the sets that contain x and y. So here, for example, if I merge, let's say 1 and 2, these two sets will become 1. And now I will have a larger set that contains both of them. Right? And then if I merge 2 and n, then this one also becomes part of the same set. And so now 1 and n are in the same set. Okay, so our first operation is merge. Our second operation basically does a query, or sometimes we will change this name later on. So it takes two elements, and you have to say whether these two elements are in the same set or not. Okay. And we'll see some examples of use cases of this later, but in this session, I'm going to mostly focus on the problem itself. So since last time we talked about amortized analysis, of course, we want to do an amortized analysis here. And since we want to do an amortized analysis, we should be able to talk about sequences of operations. So I just assume that I have a sequence of n operations. So at the beginning, I'm just given the number n. I know that my elements are 1 to n. And then I know that I will be given a sequence of n operations. These can be merge operations or query operations, and they can be in any order, basically. You're in front of the camera. Those are reserved seats. Sorry. Yeah. Okay. So how can we do this? So what kind of data structures come to mind? Well, the simplest thing that we can do is that we can just keep track of a representative for each one of our sets. So let's say that in each of my sets, I just choose one of the elements of that set, and I call it the representative of the set. And then what I do is that basically I keep track of an array. Let's call it the representative array. And let's say that its length is n. And the ith element in this representative array tells me who the representative of the set that contains element I is going to be. Okay? So I just have a simple array, and for every element, I know its representative. Okay, so what happens if I want to see if two elements are in the same set? Well, if I want to see whether x and y are in the same set, I just look at the representatives of x and y. And if they're the same, then I know that both of these elements are in the same set. Quite easy. But what happens if I want to merge two elements? Well, again, I'm showing everything based on these representatives. So if I want to merge x and y, I can first just take the representatives. So let's say Rx is the representative of x and Ry is the representative of y. And then I can just go over this whole representative array that I had here. And whenever I see Rx, I replace it with Ry. Okay. So for any I from 1 to n, if the representative of I was Rx, set it to Ry. This would, of course, solve my problem. But now let's talk about the runtimes. And I'm going to just have a table here where I write the runtimes of all of these different algorithms that we're going to have. So let's say that this is my algorithm, and this is the worst case runtime for merge, and worst case runtime for query. Okay, so my first algorithm was to just keep representatives. So what is my query runtime? We said that we just look into the representatives to see if they're the same. So this is 01. But what is my merge runtime? Well, I have this kind of stupid for loop that goes over all of my elements. So this makes it so that my merge takes order n. Okay. So now we have an algorithm where merge is costly, but query is fast. Can we have an algorithm that is the opposite of this? Can we have an algorithm where query is maybe a little bit costlier, but merge becomes fast? Now, if you think of this, we can just assume that our elements, the elements 1 to n, are just vertices of a graph. So if I have a graph with vertex set 1 to n, then whenever I do merge x, y, I can just add an edge between x and y. And if I do this, then my connected components would be my sets, right? And merging is super easy. So I can use a graph, and my connected components are my sets. So every time that I want to merge, that's 01, because I just add one edge between x and y that I wanted to merge. But what about querying? So if I give you two elements, x and y, and I ask you, are they in the same set? This question is basically asking, are x and y in the same connected component or not? And generally, you can think of our whole problem as a problem of talking about connected components of graphs. So how do you know if two elements are in the same connected component? You can start from one of them and do a DFS or a BFS and see if you reach the other one, right? So in this case, my query complexity would become order n plus m, where n is the number of vertices, which is just the number of elements in my disjoint set, and m is the number of edges. But this is not great, because just imagine if I do a lot of unnecessary merges. Then in my graph, I can have up to order n squared different edges, and that's not great, because then this one query would take order n squared, right? So I want to avoid that. So how can I avoid that? Well, we only care about our connected components, right? So just let's make sure that our connected components don't get too crowded. Let's make sure that all of our connected components are always sparse. So what is the sparsest a connected component can be? What is the sparsest a connected graph can be? It can just be a tree, right? If I have a tree on n vertices, it will have n minus 1 edges, and then my number of edges would be small. So let's say that I keep a tree. Okay. Now, if I want to keep a tree, and let's say I just give it some orientation such that one of the nodes of my tree is its root. So now each one of my connected components looks like this. I have a tree. It's not necessarily a binary tree or anything. Now, what happens when I want to do query? So if I give you two different elements, and I ask you, for example, this one and this one, are they in the same tree or not? Well, you can start from these elements, and you can just go up until you get to the root. And then if in both cases you got to the same root, you know that you're in the same tree. Otherwise, you're not in the same tree. So in other words, I'm replacing these representatives with the roots of my tree. So whenever I want to query if x and y are in the same set, I would just start from x and also from y. And from X, I go all the way up until I cannot go up anymore, and that's my root. And I do the same thing from Y, and I just check if I've got to the same root. For example, if the situation is like this, then I say X and Y are in the same set, otherwise they're not. Okay, so now my query takes order n time, right? Because I'm in a tree and I'm starting from my vertex and I'm just going up. And I can go up at most n times, n minus 1 times, right? So my query is order n. But how much time would I need for merging? So if I give you two elements, X and Y, and I ask you to merge the trees that contain X and Y. Well, the problem here is that you have to first do a query, because if they're in the same tree, we don't want to add any new edges, because that was the whole point of keeping a tree, right? So now my query is going to be at least as bad, my merge is going to be at least as bad as a query. So when I want to do merge, what I can do is, let's say, let me put X somewhere else. Let's say I have X here. I can start from X, go up to find its root. Then I can do the same thing from Y and go up to find its root. And then I just make one of them a child of the other one. Maybe I make this one a child of that one. Or I could do the opposite. I could make this root a child of this root. So what we see here is that our merge is basically the same as our query, except that we have one tiny step at the end where we connect the two roots together. So if that's the case, it makes sense to change how we do this merge. And actually, so usually they say that the merge is a query plus a link. So let's call this last operation a link operation. Okay. So whenever I say link X and Y, what I mean here is that X and Y are roots of two different trees. And I just want you to put one of them as the child of the other. Okay, so now whenever I talk about merge on trees, I'm talking about query plus link. So now I can talk about worst case runtime of link. Okay. So I didn't have this concept here, but now here it's over. So finding the roots is the thing that is taking our time, but after we find the roots, it's super easy to merge. But again, going back here, we said that we want to support a sequence of n operations. And we have operations here, at least we have this query here that is taking linear time. So if I want to do a sequence of n operations, that's going to take n squared time. And that's not great for me. So let's see if we can make it any better. Let's go back to our original idea where we had a representative for every set. Okay. So look at this merge function here. What I'm doing is that I'm taking the representative of both sets, and this is super cheap. I'm doing this in constant time. But then I'm doing this really stupid part where I'm going over everything in my sets. So I'm going over every element and I'm checking if the representative is Rx, and if so, I'm changing the representative to Ry. So the first thing we can see here is that I don't need to just go over all of the elements. It might be that the set that includes X, that set might be really small. But even when that set has 1 or 2 elements, I'm going over all of my n elements. So that's the first thing that I can fix. So what I can do is that I can just keep track of the sets. So I can have something like this. So representative of I was the representative of the set containing I. But now I can also do the opposite. Maybe I can just write set of I to be the set of all elements represented by I. Okay. So if I do this, then when I'm doing the merging here, I'm only interested in the set of elements that are represented by Rx. So instead of going over all of my elements, I just go over those elements that are represented by Rx. So I'm going to remove this one. And instead, I'm going to say for every element I that is in the set represented by Rx. Okay, what should I do now? I have to say that the representative, the new representative of I is Y, and also the set of elements that are, sorry, it's Ry, and the set of elements that are represented by Ry should also get this new element I into it. So maybe I just write that insert I. Okay. Nice, nice. So we improved this a little bit, but our worst case runtime is still not great, right? Because in the worst case, it might be the case that this set is just too large, right? So I'm getting all of the elements that were in the same set as X, which is all of the elements who were represented by Rx. And then I'm saying change the representative. But this works great if this set is small, but if this set is large, I'm into a lot of trouble. And in the worst case, this set can contain all of my elements or close to all of my elements, or even let's say half of my elements. In all of these cases, I'm going to spend linear time. So how do I make it better? So I can come up with a simple heuristic here. You see, I have two different sets. One is the set that contains X, one is the set that contains Y. I can choose which one I want to update. So I'm updating the representative of all the elements in one of these two sets, but it doesn't matter. I can merge X into Y or I can merge Y into X. They're the same thing. So I just do the one that makes the most sense. So here I can just check. I can say if the set that is represented by Rx, if its size is larger than the size of the set that was represented by Ry, then just swap Rx and Ry. Okay, so basically what I'm saying is that I always take the smaller set and merge it into the larger set. And of course, well, here I'm assuming that X and Y were not in the same set. You can do a query first to make sure that they're not in the same set so that you don't merge some set with itself. Okay. Now, does this really change our overall runtime? The idea of merging the smaller set into the larger set all the time, instead of just randomly merging? Well, it turns out yes. And this is where we get to the amortized runtimes. So let me just add amortized runtime for merge. And let's also have the amortized runtime for query. Okay. So if we look at the worst case runtime, that's not going to change. In the worst case, when I'm merging, I might be merging two really large sets. Maybe each of my sets have half of all the elements. So that's going to take linear time. But what happens when I do a sequence of n operations? So let's say I do a sequence of merges over and over again. Of course, my runtime is going to be less than n squared, but how much less? So let's look at this from the point of view of one of these elements. So for example, let's look at it from the point of view of this element. Originally, this element is its own representative because it's in its own set, right? But now what happens when we do these merges? Well, sometimes the representative of this element would change. But when the representative of this element changes, this means that two sets were being merged and this element was in the smaller set, because I'm only changing the representatives in the smaller sets. Okay, so from the point of view of this node, every time that its representative changes, the size of its set gets doubled, at least, maybe even more than doubled. Okay, so the number of times that the representative of this particular node can change is at most log n, because the set that contains this node can have at most n elements, and we're doubling each time. Okay, so if we take that, then we can say this for all of our elements. So we can say that overall, the number of times that the representative of some element changes is at most n times log n. Okay, so our sequence of n operations is also going to take a runtime of n log n, O n log n, which means that our amortized runtime is going to be, well, for query, it was O1, and we can just put O1 here as well. But for merge, I now have an amortized runtime of O log n. So as you see, a very simple idea, just this idea of merging the smaller set into the larger set all the time reduces our runtime. It doesn't reduce, of course, our worst case runtime, but it lets us have an amortized runtime of O log n. Nice. Okay. So can I do something similar with the tree? So let's forget about all of this, about having representatives and sets and merging the smaller set into the larger set. And let's say the same thing in the language of trees. So I'm going to erase this one because we're not going back to it. Okay, and remember that when we're talking about trees, we now have these two operations. So I have query and I have link. And actually, instead of query, I can also put another operation here. I can just say my other operation is find root. Okay, so find root x just takes the vertex x and returns the root of the tree that contains x. Okay, and link xy gets two vertices x and y, and we are assuming that both of them are roots of their own trees, and then merges the two trees together, connects the two trees together. Of course, we can do all of our other operations using these two, and because we're using trees, let's say that we just have these two operations now. Okay. So how can I use the same idea as before? Well, one simple thing that I can do is that I can say whenever I'm linking, I just, let's say, keep track of the size of my subtree. Okay, so for every element x here, I would just have something like, let's just call it size of x. So I have an array of size n, and size of x is the number of elements in the subtree of x. So this counts x, its children, its grandchildren, and so on until you get to leaves. Okay, now what I can do is that I can do the exact same thing as before. I can say when you want to link x and y, you have x and you have y, right? And they're both roots of some tree. So I can say just look at the sizes, and if the tree of x is smaller, then make y the parent of x. If the tree of y is smaller, make x the parent of y. Okay, so again, the same idea. We are merging the smaller one into the larger one. Now, if I do this, then again, I can talk about the same operations here. So let's, okay. I don't want to talk about merge and query anymore. So let me erase this one. I want to talk about the amortized runtime of find root. And I also want to talk about amortized runtime of link. Okay, so first of all, how much time am I spending to do the linking? That's O1, because I'm just looking at this array and figuring out which subtree is larger. And then I'm creating one pointer, basically. Okay, so our amortized link is going to be O1, and actually the real cost of linking is also O1. What about find roots? So we can do the same idea as before. And I can say that if I have some element here, and if the root of this element changes k times, each time that the root of this element is changing, the size of the tree containing this element is at least doubling, right? So I can say that the depth of my trees is going to be at most log n. And whenever I'm doing this find root, I'm basically starting from some node and going all the way up to get to the root. So it's on the amount of time I'm going to spend is or the same order as the height of the tree, which is O log n. Okay. Sorry. So because I say take one specific node and just keep track of the root of this node. That root, whenever it changes, it's because the current tree is being merged into a larger tree. So whenever the root changes, the size of the tree containing this root is doubling. So the root can change at most log n times, so the depth of this node can be at most log n. Okay. Nice, but can we do better? I'm going to show you another way that people achieve log n, and I always found this one more natural, but let me just show you that one as well before going to a better algorithm. So another way that people do this, and it's pretty similar, is that we define a rank for every element. So I can again have an array called rank. And let's say that there is a rank associated to every element. And initially, all elements have a rank of 0. Okay. And now what happens when I want to do link? So when I want to do link, if I have X and Y, and their subtrees, I look at the rank of X and the rank of Y. Okay. If one of them has a smaller rank, I just merge the smaller one into the larger one. So if rank of X is, for example, less than rank of Y, I just make X a child of Y. And I don't update the ranks at all. The only case that I update the ranks is if they have the same rank. So if they have the same rank, I then randomly choose which one I want as my new root. So let's say that I had X and Y, and let's say that both of them had rank 5. If both of them have the same rank, I just pick one of them. Let's say I pick Y and say that this is my new root. And I make X a child of Y. But after I do this, I update the rank of Y and I increase it by 1. Okay. So I can just maybe write it as a pseudocode super fast here. So let me write it here and then I'll erase it soon. So if I want to link X and Y, I do this. I say if the ranks are different. So if rank of X is larger than rank of Y, then just set the parent of Y to be X. So I just say Y dot parent becomes X. And the opposite as well. So if rank of Y is larger than the rank of X, I now say that y becomes the parent. So x dot parent becomes y. Otherwise, if their ranks are the same, well, if their ranks are the same, I get to choose, but let's say I always choose y. So again, I say the parent of x becomes y, but now I have to increase the rank of y. Okay. So this is another way of doing it. And yeah, basically the rule is pretty much the same. We're always merging the smaller one into the larger one. But now instead of looking at the size of the subtree, we're looking at this notion of rank that we had. Okay. So why is this useful? Because let's say I have some node that has rank k. Then what is the size of its subtree? So the size of the subtree is at least 2 to the power of k, right? And you can show this by induction. So originally, all of our nodes have rank 0, and they have only one element in their subtree, which is themselves. And so that's the base case of our induction. And then whenever something like this happens, whenever the rank of an element is increased, it's because it's being linked to another element of the same rank. So if this one had 2 to the power of k elements in it, and this one had 2 to the power of k elements in it, after we link, this one is going to have 2 to the power of k plus 1. And I'm just increasing the rank by 1. Okay, so this is pretty much equivalent to what we said before. And again, what can the rank of an element be? At most, it can be at most log n, right? Because the size of the subtree can at most be n. So I'm pretty sure that my rank would never increase to more than log n. And then again, I get the same runtime stack. Okay.
It's not single time operation. You said that the case must log n than single operation.
Yeah. Yes.
And then single operation is not log n.
I don't understand.
I mean, not amortized by single time operation, not log n.
Yes, probably that's. I'm not completely sure if that's true. It should be. Well, I was always thinking about amortized runtime. But yeah, yes, you're right. Yeah. So we don't need to even do amortization. Yeah, but our goal right now is to make the amortized runtime even better than this. So we're always focused on the amortized runtime. Okay. Now we have all of these. So let's see what kind of other operations we can do and how can we make this even better. So the next operation I want to talk to you about is something that we call path compression, sorry, not decompression, compression. So yeah, let's see how this works. So path compression. Here's the idea. Let's say that I do find root on this node. When I'm doing find root on this node, I have to start from here and just follow these pointers and go up to its parent, grandparent, and so on until I get to the root. So when I'm doing the find root, I'm already passing through the whole path from this node to the root at least once. So the idea of compression is that after we do this, we connect all of these nodes directly to the current root. Okay, so I go through this path, I see that all of these nodes are in the path, and then I change the parent of all of them, and I make it so that all of them are directly connected to the root. And the idea here is that, well, it's not making my current find route any worse. I mean, it's increasing my runtime by a constant factor, right? Because I was going over this path anyway, and I'm just changing the same number of pointers as I had in my past. So this is going to, let's say, change my runtime by a factor of 2 for find route. But since these paths are all shorter now, I hope that later on, when again I ask for find route from some other node, I would get to the route fast. Okay? And actually, this doesn't only affect the nodes that are on this path, it can affect a lot of other nodes as well. So let's say if this node has another child and maybe that one also another child. So, or okay, that wasn't a good example, sorry. So, okay, let's say this one has another child. Then previously this child had to go here and then go up all the way, but now it goes to its parent and then directly to the root. So we're actually making a lot of our paths really shorter by doing this path compression. Okay, but does this affect our overall runtime? So let's say that I have two ideas now. I have two heuristics. One is this idea of link by rank, which says you always link the elements with the smaller rank into the element with the larger rank. And the other idea is this idea of path compression. So I'm applying both of them now. So let's look at the runtimes here. So link is going to take constant time anyway, right? Because it's just changing one pointer. So what happens to find route? So I know that just by using this one, find route is going to take amortized time O log n. But how can I say that the path compression actually helps? So before I can show that to you, I need to define a new function. So where should I put it? Yeah, maybe I can erase this one because we all know what our problem is now. Okay, and these were our operations. Okay. So here's the function that I want to define. I want to define a recursive variant of log, which I call log star. And log star of n. Okay. Think about how log itself works, right? So if you think about log, it's basically counting the number of times that you have to multiply by a certain factor to get larger than that. But now what happens if we take this same idea and say, I want to look at the number of times that I can take the logarithm. So log star of n is the number of times that you have to take the log of n until you get to something that is less than 1. Okay. So if I want to formally define it, I would say that log star of n is 0 if n is at most 1. And otherwise, it's 1 plus log star of log of n. Nice. Okay, so this is how I'm defining log star recursively. Okay. So to give you some examples, log star of 2 would just be 1 plus log star of log of 2, which is 1 plus log star of 1. And log star of 1 is 0, so log star of 2 is just 1. Okay. Now let's say I want to compute log star of 2 to the power of 2. This would be 1 plus log star of 2, and log star of 2 was 1, so this is 2. And I can continue like this. I can say the log star of 2 to the power of 2 to the power of 2. This is going to be 3. Right? And generally, so this is the intuition that I want you to have for the log star function. Log star of 2 to the power of 2 to the power of 2, so on. If I have a tower of exponentials and the size of my tower is k, then the log star of that huge number is going to be k. Okay? So the log star function is a very slowly growing function. And for anything that you would use in the real life, I would say its log star is definitely not going to be more than 10. Okay? So now what do I want to do? I want to say that if I do n of those operations, and again, I don't care about the link operation that much. So let's say if I do n of the find root operations, I want to say that my overall runtime is order n times log star of n. Okay? So this is my claim. A sequence of n operations takes order n times log star of n. Okay, so before proving this, I just want you to appreciate how close to linear this is. It's like if you have n elements, what does that mean? That means that you can at least probably store these n elements into your memory, right? So this log star of n in practice can at most be the log star of the amount of memory that you have on your machine. And again, for any real world value, that's not going to be more than 6 or 7. I don't even think it can get to 6 or 7. So practically, if I have an algorithm that has this kind of runtime, it's really going to be indistinguishable from an algorithm that has linear runtime. But theoretically, the runtime is not linear, okay? Because this thing is not a constant. Okay. So let's prove this. Let me actually use the notions that I have already defined to prove this. So let me erase this one. So our first point was that we just proved that if an element has rank R or whatever, if it has rank K, then it has a subtree of size 2 to the power of K at least, right? So here's my question. How many elements of rank K can we have? Or actually, let me see if I use, yeah, I use R. Okay, so how many elements of rank R can I have? So I know that every element of rank R has a subtree of size 2 to the power of R, right? But the problem is, can an element of rank R be in the subtree of another element of rank R? Not really, because then in that case, the root would have rank at least R plus 1. So the way we defined our ranks here in our linking makes sure that if I look at the elements that have rank R, their subtrees are completely disjoint, right? And each of these subtrees has at least 2 to the power of R elements in it. And totally, I have n elements. So I can have at most n divided by 2 to the power of R elements of rank R. I can have at most this many elements at any time, right? But what if I ask you overall? So what if I ask you to just look at all of the elements and count all those elements that at some point during these operations had rank R? How many elements like that can we have? So I know that at any given time, I can have n divided by 2 to the power of R elements of rank R. But what if I look at all of the elements that were of rank R at some point, not necessarily right now at the same time, but at some point? So if you look at those elements, and if you again look at how we were defining our ranks, you see that our ranks are always increasing. They're never decreasing, right? So if I have an element that at some point had rank R, at the end of all of this sequence of operations that I'm doing, it will have a rank of R or higher, right? So I know that there are at most these many elements that can have rank R at the end. And so I can write this for rank R plus 1. I can also write it for rank R plus 2, and so on. Right? And we will see this sum over and over again. It's just something, and then that thing divided by 2, the same thing divided by 4, and so on. So this is at most twice the original value. So it's 2n divided by 2 to the power of 1. Okay, so if I count all the elements that at some point had rank R, their total number is going to be at most this much, or n divided by 2 to the power of R minus. Okay, so just keep this lemma in mind. And let's do something else with our elements. I want to divide my elements into groups, and I want to do it based on the log star of their rank. Okay, so I will have a bunch of groups, and let's say I have a group, and these are the ranks that are allowed in that group. So my first group, or maybe let me see if I can give you a better picture. Okay, let's say that I have, okay, let's say I have a bunch of groups, and I'm dividing my elements between these groups. Okay, but I'm doing them based on their rank. So the first group would consist of all the elements that have rank 0 or 1, let's say. Or maybe I can just say rank 0 here, rank 1 here, rank 2 and 3 here, and so on. So the idea is that if I look at the log star of the rank, these are the elements whose, okay, yeah, 0 is not very great, but okay, the 1, these are all the elements where the log star of the rank is 0. These are all the elements where the log star of the rank is 1. Then in the next group, I will have all the elements where the log star of the rank is 2, and so on. And I have as many groups as I need to cover all of my n elements. Okay, so generally, I would show these groups like this. I would say that this group is from rank I to rank 2 to the power of I minus 1. Right? Because that's how log star changes. So log star of 2 to the power of I is 1 more than log star of I. So I will have all the elements here whose rank is from some I to 2 to the power of I minus 1. Okay, the first thing I want to ask you is how many groups do I have? What is the total number of groups that I can have? Yes, it's log star n. Because so if you look at the rank of these elements, what can my ranks be? They're definitely always at most n, right? Actually, we showed that they're order log n, but they're no more than n. And if they're no more than n, their log star cannot get more than log star of n. So the number of different groups that I have is at most log star n. Maybe some constants, but I don't really care about constants. Okay. So now finally we can go and look at what happens when we do find root. So let's say I'm doing a series of find root operations. What am I doing in these operations? I'm basically starting at some vertex and traversing some edges that go up until I get to the root, right? And what I want to do is that I want to count how many edges I'm taking overall. right? So in every single operation, I know that the number of edges that I take might be large, but I want to count what is the total number of edges that I take and go up in all of my n find root operations. Okay, and I don't count the parts where I'm changing these because this is just a constant factor. Okay, so when I want to analyze my runtime, I only analyze the number of edges from some vertex to its parents that I have taken. Okay, so let me now erase this one. Okay, so what do I want? I want the total number of edges from some vertex, let's call it u, to u dot parent that I have traversed. So that were traversed by n times execution of find root. So I did n find root operations, and I want to find the total number of edges that went from one vertex to its parent. Okay. So what can I do? I can say that there are three cases for an edge that goes from a vertex to its parent. Either the parent is already the root. So the first case is I'm at an edge and its parent is the root, and I've taken this and I've got to the root. Okay, so I call this E1. So E1 edges are the edges where u dot parent is root. Plus. Now I come back here and look at these groupings that I had. So if I take an edge, I'm either taking an edge from one of these groups to the other one, to the one above it, or I'm taking an edge between two vertices that are in the same group. Okay, so I'm going to say, let's say my E2 edges are edges where this vertex u and its parent are in different groups. Okay, and then I have E3, which are the edges that are in the same group. So u and parent in the same group. And of course, this is also assuming that the parent is not the root. So the case where the parent was the root is in E1, and in E2 and E3, none of them are the root. But in this one, I'm going between groups. In this one, I'm inside the same group. So let's just find bounds on the size of each of these sets. Okay. So how many edges of type E1 can we possibly pass through? So I have n find root operations, and each find root operation has at most one edge of type E1, right? Because that happens when you're at a child of the root and you go to the root. So overall, the number of E1 edges is going to be On. How about the E2 edges? So how many times can I go between different groups? So as I do this find root, I start somewhere in my tree and I just keep going up. And as I'm going up, the rank is never decreasing. So the rank of this node, as I go up, it's only ever increasing. Okay. So it can start in one of these groups and it can increase all the way to the highest group. But in every find root, I'm going to go between groups at most log star of n times, because I have at most log star of n groups and I'm going in order, right? So the total number of E2 edges, the edges that go between groups, is going to be order n log star n. Okay, this is good. So now if I can find a similar bound for E3, we're done, right? So if I can say that the total number of edges that go in the same group is also at most n times log star n, then I would be happy. Okay. So what would I do with the edges that go in the same group? Here's what I would do. I say, look at it from the point of view of one vertex again. Okay. So just fix some vertex u. And let's say that I have a group here. And let's say that this group is between ranks of between I to 2 to the power of I minus 1. And let's say that I have this vertex u in here. Okay. I want to see how many times I can traverse the edge between u to its parent while remaining in the same group. Okay. And of course, I'm also assuming that the parent is not the root. So in other words, how many times can I change the parent of u? I'm doing path compression, right? So when I'm doing path compression, actually the parent of u can change a lot, right? So I can connect u directly to the root, and then maybe later on the root of the current node changes, and then when I get to u again, I might have to create a new connection to the new root and so on. So I can have a sequence of parents for u. So consider all the parents of u where I've traversed the edge from u to that parent, and let's call them P1 to Pk. So P1, P2 to Pk are parents of u. And these are at different points of time. That's why I don't have a unique parent, of course. Now, what can you say about the rank of P1 to Pk? Well, first of all, we're only counting the cases where the rank is in the same set, is in the same group. Okay. But what do I know about these ranks? Do I know, for example, that these ranks are increasing? Yes, because I don't care about the first parent, but the second parent is basically the root of the subtree that u was in, right? And then the next parent is the root of an even bigger subtree, and so on. So these ranks are actually increasing. So in other words, none of the parents of u have the same rank. Okay. And all of them have ranks that are between I and 2 to the power of I minus 1. So how many parents can you have? Well, at most the same number of elements that we have here, right? So number of parents of u is at most, well, I'm just going to call it 2 to the power of I. Right? Because, yeah, it's 2 to the power of I minus I, whatever, but that doesn't really matter. What we really care about is the largest thing there, which is 2 to the power of I. Okay, so now I can sum this up over every value of u. Okay, so I can say this. I can say that my total number of edges of this type 3. Now I have to find somewhere else to erase. Okay, let's erase this one. Okay, my total number of edges of type 3 is at most what? Well, I can sum over all of my groups. And let's say that my group went from, let's say, I to 2 to the power of I minus 1. And then I have to sum over all the u's that are in this group. And then what is the number of parents? It's at most 2 to the power of I. So I want to find a bound for this sum. Any ideas? Yeah, of course, it's n log star n. But here's the thing. How many elements u do we have here? Because you see, this sum is just the number of elements u that we have times 2 to the power of I. So after I fix the group, I'm just summing up 2 to the power of I for every element of it. So how many elements can I have in this group? Yes, it's just this thing here, right? So the number of elements that I can have in this group is the number of elements of rank I plus the number of elements of rank I plus 1 plus the number of elements of rank I plus 2 and so on. So it's at most the sum. I'm going to put this one here, I to 2 to the power of I minus 1. So I have 2 to the power of I times, okay, how many elements of size I could I have? It's 2n divided by 2 to the power of I. How many of size I plus 1? 2n divided by 2 to the power of I plus 1, and so on. And it ends at some point when it gets to this. Okay, but again, we have this sum, this really nice sum where everything is just being divided by 2. Okay, so this is less than or equal to, I'm going to write the first part again, sum over this group G that went from I to 2 to the power of I minus 1. I have the 2 to the power of I there, and I have twice this thing. So I can just say 4n divided by 2 to the power of I. Okay, so I get rid of these. So now I have a sum over all of my groups. And for every group, I'm paying a cost of 4n. So the number of our groups was at most log star of n. So this sum is at most 4n log star of n, which is O n log star of n. Okay, so that's it. That's the proof here. So if you do pass compression, and if you also use this idea of always merging the tree with the smaller rank into the tree with the larger rank, you can guarantee that your overall runtime is at most n log star n. Now, if the overall runtime is n log star n, then the amortized runtime for one find root operation is just log star n. Okay, so we could start from a case where we had to spend an overall runtime of order n squared. Then we had a very simple heuristic, merging the smaller set into the larger set. This got us down to order n log n. And then we had another simple heuristic, which was this idea of compressing the paths. And this got us down to n log star n. Okay. And honestly, here, like implementing these algorithms is super easy. Really, the hard part is the analysis. Like the algorithm itself is very easy and straightforward. Okay. Now we have a tiny bit of time. So let's talk. Well, you can actually put m there, but then it would become m times log star of n. Like the same analysis would go through.
But then it would be log star n.
Yes. Yeah. So the amortized runtime at the end would be log star n. I don't want to have too many parameters, so I always just assume that the number of operations is also n. But all of these ideas would work even if you have a different number of operations. Okay, we have 15 more minutes. Let's try to do one more algorithm. So I want to talk a little bit about minimum spanning trees. Or MST. So let's say that you have a graph and it's an undirected graph, but it's connected. And let's say that every edge has a weight as well. And we want to remove as many edges as possible. We want to make sure that we minimize the sum of the total weights of our edges in a way that keeps the graph connected. Okay. So the story that people say about this usually is that you have a set of n cities and you know the cost of creating a road between any two cities, and now you want to be able to connect all of the cities together with the smallest possible cost. So both of these cases get us to what we call a minimum spanning tree. So given a connected graph, a spanning tree is a tree that touches every node of the graph. Okay, and a spanning tree on a graph with n nodes will of course have n-1 edges. So we want to find a spanning tree that has the smallest total weight given some graph. Now, the lemma that we usually use is something called the cut lemma. So let's say that I have my graph G, and let's say my vertex set is V and my edge set is E, and let's say there is a weight on every edge. Suppose that I just arbitrarily divide my vertex set into two different sets. Okay, so let's say that I take the set X, which is a subset of my vertices, and let's say that I take another set, which is the complement. So V minus X. Okay, and I look at all the edges that go between these two sets. So there might be a lot of edges. I look at all the edges that are going between here and here. And I look at all of their weights. So let's say this has weight 2, this is 4, this is 5, this is 1. Oh, okay, no, this is 6, this is 7. Okay. So I look at all these weights and I take the minimum. Now, the claim that I want to make is that there is always a minimum spanning tree that contains this minimum edge. So no matter how you divide your graph into two sets of vertices, after you do the division and after you look at all the edges that go from one set to the other, you can always take the minimum weighted edge that goes from one set to the other, and you can always be sure that there is a minimum spanning tree that contains that particular edge. Okay, so how do we prove this? Actually, the proof is super easy. So let's say that I have a minimum spanning tree, and let's say that it doesn't contain this particular edge. Okay, so it has to connect all the vertices here. Right? It has to connect all the vertices here. So somehow it connects all of them. And let's say, yeah, whatever. So if I have a minimum spanning tree, it has to connect all the vertices on this side and all the vertices of this side. And of course, it has to connect the two sides. So there should be at least one edge that goes from this side to that side. Let's say that it wasn't the minimum edge. Let's say it was this edge. So what I can do is that I can just remove that one and add the minimum edge, right? And this decreases the total weight of my spanning tree. So this shows that either it wasn't a minimum spanning tree, or actually there are cases where you have more than one edge that has the minimum weight here, then you can pick which one you want to have in there. But the important point here is that in any cut set like this, in any division of the graph to two parts, you can always take the minimum edge that goes from one part to the other part, and you can always be sure that there is a minimum spanning tree that contains that edge. Okay. And I'm very careful about how I'm phrasing this because the minimum spanning tree is, of course, not unique. You can have many different minimum spanning trees. Okay, now we have this. So using this, I want you to find an algorithm for finding minimum spanning trees in a graph. Now that I've given you all these ingredients, it's kind of obvious. And the algorithm is actually named after Kruskal. So this is Kruskal's algorithm. And what we do here is that we start with an empty graph and we sort our edges based on their weight. And we start from the cheapest edge and we just go forward and try to add these edges. So whenever I get to an edge, either this edge connects two different connected components, in which case, according to this lemma, I can always put this edge in and be sure that I'm having a minimum spanning tree. Or both sides of the edge are in the same connected component, in which case I wouldn't add the edge. So that's Kruskal's algorithm for finding a minimum spanning tree. So I can just write some pseudocode here. So this is Kruskal. Let's say I have a graph G, which has vertex set V and edge set E. And let's say I have a weight function that assigns some positive weight to every node. And what I'm going to do is to just sort my set of edges E by weight. So from smallest weight to largest. And then I'm just going to go over this sorted list in order. So for every E in E, in the order that we have sorted them. So we just check if the two sides are in the same connected component. And we're going to use a disjoint set data structure to do that. So I just say, okay, let's say that this vertex, this edge E was from vertex U to vertex V. I just say if you query U and V and they're in the same set, then do nothing. Otherwise, if they're not in the same set, add this edge E to the minimum spanning tree and also merge the two endpoints. Okay. So now if I have n vertices and m edges, what is the runtime? Using the algorithm that we just saw, well, we will do at most m merge operations, m merge and query operations overall, right? Because I'm doing one operation for, or at most two operations, let's say. I'm doing order m operations overall because I'm doing at most O1 different operations for each edge, right? And we saw that our operations took log star n time amortized. So overall, my overall runtime is going to be m times log star of n, which is, again, this is a great runtime because m is the number of edges that we have. So just by reading the graph, I'm going to spend OM time. There's no way I can have an algorithm that spends less than OM. I have to at least store my edges, right?
You also have to sort it.
Yeah, oh, yes, sorry, I forgot that one. Yeah, and then we're just having log star n, but there is also the sorting at the beginning, which takes m log m. Yes. So we couldn't get better than m, but now we are away but by only a factor of log n. Right, and actually the part that's taking most of the time is the sorting at the beginning. Okay, great. So I have 5 more minutes. I can also tell you about another algorithm for the same problem. And this connects us to the topic of the next session. The next algorithm we have for the same problem, for the problem of finding minimum spanning trees, is an algorithm by Prim. And the idea is a little bit different. The idea is that here we used to keep track of several different connected components. And every time we try to find an edge and merge two of our current connected components. In Prim's algorithm, we will always have just one connected component. So the idea is that I start from vertex number 1, and I say my connected component is just this one vertex. So I put this one vertex on this side and everything else on the other side. So this tells me that I have to look at the cheapest edge that goes out of this vertex. So I take that cheapest edge, and I know that that edge has to be in my minimum spanning tree. So I just add that edge and its other side to my minimum spanning tree. Okay. Now I say that my connected components consists of these two vertices. So again, I put these two vertices on one side and every other vertex on the other side. I find the cheapest edge, I add that cheapest edge and the other endpoint of it. And I just keep doing the same. So
part of the build tree in this lemma, we don't have tree at all. So lemma say nothing about building tree after we have some part of tree.
right. Again, I don't understand.
In lemma, we don't have any partially built tree.
No, so in the lemma, we're just saying that whenever we divide the set of vertices in two sets, we can take the smallest edge that goes across, and that's going to be in a minimum spanning tree.
So we have some edge fixed.
Yes, but the edges that we fixed were guaranteed to be in a minimum spanning tree. So it's fine. I can just continue adding them. Okay, so every time I'm finding an edge, and I'm guaranteed that that edge is in a solution. And even if I have part of the solution, I'm guaranteed that that edge, that I can extend my partial solution using that edge. It's the exact same idea here. So yeah, the difference is that instead of keeping track of several connected components, Prim keeps track of only one connected component. But now each time we have to find the cheapest edge that goes out. And for that, we're going to see some data structures on the next session. So that's all for this session, and have a great time.